Hello and welcome back. This is my favorite part of the power function series. I'm going to talk about some applications. So just to get started here, um, one application I have is Newton's law of gravitation. Now, I'm sure many of you have not taken physics, so I'm not going to get into any specifics. I really just want to focus on the math of it. But there's this equation that says the force of gravity between two objects. So all objects of mass in the universe experience a attractive force to one another. So even you and I, and me and this pen right here. So those are just some examples. But if you look at the screen, we have a blue mass and we have an orange mass, and they are at some distance apart, and they are experiencing an attractive force. And that force is equal to a gravitational constant, which is just some crazy number, times the masses multiplied, and then divided by the distance between them squared. So that's just what the function says. And so you might be wondering how this is a power function. So let me write it a different way. You scroll down here. So if you look on the left, you could also write this as F equals K times R to the negative 2. And I'll explain how I got that. So in part 1 of the series, I talked about how if you give your input, your x value, a negative exponent, you can make that exponent positive by just flipping it to the bottom of the fraction. So I just kind of did the reverse here. I said 1 over r squared is the same thing as r to the negative 2. Now, what about the k? Well, if I look at this numerator right here, g is a constant, it doesn't change, and then the masses of the objects are not going to change. So I just kind of grouped all three of those terms together, and I said that's my constant, that's my coefficient in this function. So this is an example of a power function, and so I also wanted to show you kind of graphically what this could look like. So first thing that I did was I wanted to know what kind of force I experience with the Earth. So I took my mass in kilograms and I multiplied it by the mass of the Earth in kilograms. And then I multiplied all of that times big G, the gravitational constant. And I got this number. I got this number right here, 2.4 times 10 to the 16th. So that's my K, that's my constant. And then I wanted to know how my force that I experience with the Earth varies with radius. Now, keep in mind that the force of gravitation, or the force of gravity, it acts from the center of mass. So I didn't modify my radius at all, which means I'm kind of looking at the force I would experience with the Earth if I was at like close to the core of the Earth, which I don't think I'd experience any force because I'd be burned to pieces. But this is hypothetical. So what I did here was I graphed this function in blue, and I can't have a negative radius. So kind of like in my domain videos, I had to restrict my domain according to the context. So r is going to be greater than 0 was another parameter I put in. And if I hadn't done that, I would have gotten like kind of the symmetry right there. But anyway, so force is on my y-axis, radius is on my x-axis. And so I can see that the closer I am to the core of the Earth, the more force I'm experiencing. That is too much for someone to handle. But then as I move away, as my radius gets bigger and bigger, my force goes down. And so a power function models the force of gravity. And okay, so that was example number 1. And then we're going to do some more physics. And this is also kind of related to Newton's law of gravitation, so that's cool. But I want to talk about Kepler's third law. And so something about power functions, when you're using them in the real world, is that they show variation. So in the last example, when my radius increased, my force decreased. So when I kept my constant the same, of course. So that is known as indirect variation. When one variable goes up, the other goes down. And Kepler's third law is an example of direct variation. So I don't want to go into the specifics just because it deals with ellipses, and you learn about that a little bit later. But if you have a planet orbiting the sun, Kepler's third law says that the period squared equals some constant times the semi-major axis cubed. Okay, so let's break that down a little bit. So the period is referring to the orbital period. It is the amount of time it takes the planet to do one orbit around the sun, just like a revolution, basically. And the semi-major axis, it's just a property of the orbit, but for our purposes, let's call it distance. So A is the planet's distance from the sun. So that's that relationship there. So power functions will show direct or indirect variation. In this case, we're looking at direct variation. As our distance increases, our A increases, so does the period. That's basically what this equation is showing us. And we might also want to put that in, language we can understand. Basically, that's saying the farther away the planet is from the sun, the longer it'll take to make an entire orbit around the sun. So that's kind of like putting our direct variation into words. And we can kind of see this. I have a picture here from the European Space Agency. It's a little diagram. And it shows how we have these different planets in our solar system that are in these concentric paths. And so you can infer that the ones that are farther out, they have a greater A value. They have a greater distance. And what this law tells us, it means that the planets that are farther out are going to take more time to get around the sun. So if you want to test this, you can look up the orbital period of some of the planets and compare them. So if you look at Saturn, for instance, Saturn takes 29 Earth years to make a full orbit, versus Earth takes 1 Earth year. And that's because of that, that difference in distance, because of this law. And this one's actually cool because Newton's law of gravitation is the driving force behind this phenomenon. So that's just physics. But anyway, so those are some pretty cool applications of power functions. We see that they are really useful for showing how different variables relate to each other. And we also might have a huge formula like Newton's law of gravitation. But if we really look at it, we can just break it down into a simple power function. So I appreciate you watching this series, and I hope you enjoyed.